We studied direct current earlier. Direct current does not change direction with time. However, most appliances in our daily lives run on voltages and currents that vary with time. A time-varying voltage that varies like a sine function is called alternating voltage or AC voltage, and the current driven by it in a circuit is called alternating current or AC current. The term AC is actually universally used to refer to any electrical quantity that varies with time, just like simple harmonic motion that is related by a sine or a cosine to time. In circuit diagrams, AC voltage is denoted by a sinusoidal wave in a circle. Electrical energy supplied to consumers is transmitted and distributed through power grids as alternating current. AC is preferred to DC mainly because AC voltages can be easily and efficiently converted from lower to higher voltages and vice versa using transformers. Let us study what happens when an AC voltage source is connected in series to a resistor with resistance R. The potential difference provided by the AC source is expressed as V is equal to Vm sin omega t. Here, Vm represents the amplitude of the voltage and omega represents the angular frequency of the oscillations of the potential difference. Angular frequency omega should not be confused with frequency. For example, the AC voltage supplied to our households has a frequency of 50 Hz. This means the angular frequency is 100 pi radians per second. We can calculate the current passing through the resistor using Kirchhoff's loop rule. The algebraic sum of all the potential differences across various components in the circuit is equal to 0. A proper sign should be used for potential differences around the loop. Applying Kirchhoff's loop rule to the given circuit, we get Vm sin omega t minus IR is equal to 0, where Vm is the maximum potential difference offered by the AC source. Here, Vm sin omega t is the potential across the given voltage source. The second term IR is due to the fact that if a current of magnitude I passes through a resistor of resistance R, the potential fall across it can be denoted by the term IR. Solving this equation, we get the expression for current as I is equal to Vm by R into sin omega t. As the magnitude of the resistance of the resistor R is a constant, the equation is simplified to I is equal to Im sin omega t. Here, Im is the amplitude of the current denoted by the fraction Vm by R. The graph of the current passing through the resistor and the potential difference across it against time is as shown. Here we observe that the magnitude of the current flowing through the resistor and the voltage across the two ends of the resistor reach their maximum values at the same time. They also reach their respective minimum values at the same time. In fact, these values even reach 0 at the same time. This implies that in a pure resistor, the current flowing through the resistor is in phase with the potential difference across it. The fact that the current and voltage are in phase can be seen more clearly if we divide the instantaneous voltage V by the instantaneous current I. Therefore, the ratio of the instantaneous voltage V and instantaneous current I is a constant of magnitude R. This means that the ratio of voltage to current is constant. Hence, Ohm's law is valid in the case of resistances connected in a circuit with an AC voltage source. As the AC current flow across a resistor varies with time in a sinusoidal fashion, its magnitude takes both positive and negative values. Here, all instantaneous current values over a cycle add up to 0. Therefore, the average current is 0. However, the average power across the cycle is not 0 since the power dissipated across the resistor is proportional to I square. As I square always assumes a positive value even when the value of current is negative, the average power is always positive. We know that electric current refers to the flow of electrons in a circuit, and the direction of the current is conventionally taken to be the one opposite to the direction of the flow of electrons. As electric current passes through a resistor, the resistor gets heated. This is due to the collision of electrons with other electrons and atoms, and the constant acceleration and deceleration of electrons due to a reversal in the direction of the flow of current. This heat dissipation across a resistor due to the electric current through it is also known as Joule's heating, which is expressed as I square R. The instantaneous power dissipated in the resistor is I square R. Earlier, we learned that the current through an AC circuit containing a resistor is given by I is equal to Im sine omega t. On substituting the value of I in the equation for power, we get P is equal to Im square R sine square omega t. If we average the value of the instantaneous value of power over an entire cycle, we can write the expression as shown. Here, the quantity P bar denotes the average value of power. Conventionally, an average of values is shown with the bar over the quantity symbol. The angular brackets denote the average of the quantity inside the brackets. As the quantities Im and R are both constant, we can take them out of the angular brackets while computing the average value of the expression. Now, we have to calculate the average value of sine squared omega t in order to compute the average value of the expression. For this purpose, we will use the trigonometric identity. Sine square omega t is equal to half of 1 minus cos 2 omega t. Therefore, the average of the required expression is given as shown. However, the average value of cos 2 omega t over a complete cycle is 0. This makes the average of the sine square omega t over a cycle as half. Therefore, the average power dissipated over a cycle is half of Im square R. If we define a new value of current to be associated with AC, that is, Im by root 2, we can get the expression of power dissipated from a resistor in AC current in the same way as in DC current. That is, I square R. This new value of the current is called root mean square. In short, RMS current, denoted by IRMS or effective current. RMS current is defined as the root of the mean of the square of current. For a sinusoidal current, its value is 1 over √2 times or 0.707 times the amplitude of the AC current, IM. The average power dissipated by any form of AC current in a resistor is IRMS square R. Similarly, we can denote the RMS voltage or effective voltage, VRMS, as Vm by √2, where Vm is the amplitude of the AC voltage. The value of voltage normally used to describe an AC voltage is an RMS voltage. For example, domestic supply has 220 volts AC. Here, 220 volts is the RMS value of the voltage given to domestic consumers. The amplitude of the AC is √2 times the value of RMS voltage. Thus, the amplitude of the AC given to domestic consumers is approximately 311 volts. In our study of AC current applied to a resistor, we found that the voltage and current through a resistor are in phase, which is not always true. That voltage and current through a resistor are in phase was based on an assumption that there are only resistors in the circuit. Normally, circuits are made up of inductors, capacitors, and other elements. To study such complex circuits, where elements other than resistors are also present, computing values becomes an arduous task. Thus, we use the notation of phasors, which significantly simplifies the calculations involved in solving such complex circuits. A phasor is a representation of a sine wave whose amplitude, phase, and frequency are time invariant. We can visualize a phasor as a phase vector that rotates about the origin with an angular velocity omega. Thus, the phasor of a wave is a vector that has a magnitude equal to the amplitude of the wave and that rotates around the origin with an angular velocity equal to the angular frequency of the wave. To get the physical values of the sinusoidal varying quantities, such as AC current I and AC voltage V, we take the vertical component of the phasors, I and V, respectively. The magnitude of phasors, V and I, signifies the maximum or peak amplitudes of the quantities specified by the phasor. However, the instantaneous projections of these phasors give the instantaneous values of the quantities that they represent. The phasors for V and I, in the case of a resistor, are always in the same direction. This means they are in phase, or the phase angle between them is 0. An inductor or a solenoid is an electrical component that can store energy in the magnetic field created by a varying current flowing through it. It is typically a wire wound around a ferrite core. An inductor resists any change in the current flowing through it. Any change in current through an inductor induces an EMF across it. This induced EMF is proportionate to the rate of change of current. According to Faraday's law of electromagnetic induction, the induced EMF in an inductor is equal to minus L di by dt, where L is the self-inductance constant for the inductor, and I is the amount of current passing through the coil. This EMF opposes the change in current flow through it in accordance with Lenz's law. Hence, a minus sign as per convention. Now, we shall see how an inductor behaves when an AC voltage is applied across it. Let's assume that the inductor coil has negligible or zero resistance. This assumption is mainly so that we can observe how an inductor ideally behaves. Now, assuming the circuit to be purely inductive, we shall make use of Kirchhoff's loop rule. According to this rule, the sum of potential differences across various components is zero. The voltage across the source of alternating current is V equal Vm sin omega t, where Vm is the amplitude of the AC voltage and omega is the angular frequency and t is the time. Let this be equation 1. Applying Kirchhoff's law to the purely inductive circuit, we get Vm sin omega t minus L di by dt equal to 0. Here, Vm sin omega t represents the potential difference applied across the circuit, and the term L di by dt represents the self-induced EMF in the inductor. Thus, we get di by dt to be equal to Vm by L sin omega t. Let this be equation 2. Equation 2 is a simple differential equation. It tells us that the first derivative of the current with respect to time is a harmonically varying quantity with an amplitude Vm by L and an angular frequency omega. This implies that this derivative is in phase with the applied potential difference. Integrating equation 2 with respect to time, we get the value of the current in the circuit as I is equal to minus Vm cos omega t by omega L plus the constant of integration. Let this be equation 3. Since we know that the voltage source is supplying a time-dependent voltage, which is symmetric about 0, we can assume the same to be true of the current. Hence, we take the constant of integration as 0. Hence, equation 3 can be written as I equal to minus Vm cos omega t by omega L. Let this be equation 4. Writing minus cos omega t as sin omega t minus pi by 2, we get I equal to Vm by omega L into sin omega t minus pi by 2. Let this be equation 5. Now we substitute omega multiplied by L with XL, which is known as the inductive reactance of the circuit. We get the amplitude of the current, Im equal to Vm by omega L or Vm by XL, since we know it to be the maximum current value attainable. Hence, equation 5 now becomes I equal to Im sin omega t minus pi by 2. Let this be equation 6. The expression we used earlier for Im implies that the value of current in comparison with the value of voltage is limited by the denominator, which we call the inductive reactance of the circuit. This by analogy for a simple resistive circuit can be considered an equivalent to resistance. This inductive reactance is directly proportionate to the inductance L of the circuit and the frequency of the current or voltage. Inductive reactance is equal to 2 pi LF, which is equal to omega L, since 2 pi F is equal to omega. On close inspection of the expression derived for the value of current in the circuit, we can see that the current lags voltage by a factor of pi by 2 in phase. The phasor diagrams to analyze the relationship of lead or lag between the current and voltage is shown. The current lags behind the voltage in phase by pi by 2 or in time by 1/4 of the time period t. Another observation is that the maximum value of the current in the circuit is achieved at exactly 1/4 the time period of every cycle. Let us now try to see the power dissipation through the inductor compared to resistance. The instantaneous power supplied to the inductor is denoted by the product of voltage with current flowing through any circuit element. By substituting for V and I as in equations 1 and 6, we get P is equal to Vm sin omega t into Im sin omega t minus pi by 2, which is equal to Vm Im sin omega t into sin omega t minus pi by 2. As sin omega t minus pi by 2 equal to minus cos omega t and 2 times sin omega t into cos omega t is equal to sin 2 omega t, we get power P equal to minus Vm Im by 2 into sin 2 omega t as shown. Let this be equation 7. This instantaneous power evaluates as a time-dependent harmonic function. As this is a time-dependent sinusoidal function, its average over one complete time period will be 0. The argument of sine function for voltage is omega t, and for power is twice omega t. Hence, the time period for the power function is half the time period for voltage. Since the average value of sin 2 omega t over one complete cycle is 0, the power supplied to an inductor on average in an AC circuit over one complete cycle is 0. This can be seen as displayed by the plot of power supplied versus time. Variation of voltage and current with time is also plotted on the same graph for comparison. As the inductor is nothing but a coil of wires, it is structurally the same as an electromagnet. Hence, when the current flows through the coil, it is magnetized and demagnetized depending on the direction and magnitude of the current in the circuit. Variation of magnetic flux with time too is plotted on the same graph. As shown in the graph, we will study the magnetization of the inductor in the 4 periods marked in the graph as 0, 1, 1, 2, 2, 3, and 3, 4 respectively for one complete cycle of voltage or current. As in the first time interval 0, 1, the value of the current keeps rising from 0 and reaches its peak value at 1/4 of its time period. The flux passing through the coils change, setting up a magnetic field as shown in the figure. The current enters the inductor coil at A and leaves at B. As the current and voltage are both positive. It means the power is positive. Positive power means the inductor is absorbing energy from the circuit. In the second time interval, 1, 2, the value of the current keeps decreasing from its peak value at 1/4 of its time period and reaches 0. But it always remains positive. The flux passing through the coils change, decreasing the magnetic field setup as shown in the figure. As the current is positive while the voltage has become negative, it means the power is negative. Negative power means the inductor is releasing energy to the source, which is the circuit. During the third time interval 2, 3, the values of both current and voltage are negative. Since the current has become negative in this interval, the flux passing through the coils change, setting up a reverse magnetic field as shown in the figure. In this case, the current enters the inductor coil at B and leaves at A. As the current and voltage are both negative, it means the power is positive. Hence, energy is being absorbed by the inductor. During the last time interval, 3, 4, the value of the current decreases and reaches 0. As the current is negative, while the voltage is positive, it means that the power is negative. Hence, energy is again being released from the inductor. This cyclic discharging and charging of the magnetic field of the inductor in reverse polarities keeps on taking place as long as there is AC current flowing through the inductor. Thus, the instantaneous power in the inductor is positive when both the instantaneous voltage and the instantaneous current are positive or both negative, and the power is negative when any one instantaneous voltage or instantaneous current is positive and the other negative. A capacitor is a device that can store a charge. A simple capacitor consists of two conducting plates separated by an insulating material called a dielectric. Unlike an inductor, which resists any change in current, a capacitor resists any change in voltage, thus ensuring a supply of constant voltage. Let us understand what happens when a capacitor of capacitance C is connected to a DC voltage source of potential difference V. When the key is closed, the capacitor gradually builds up charge as current passes through it. If the charge on it at this instant is Q, then the potential difference across its plates in the steady state is V is equal to Q by C. As plate A of the capacitor is connected to a positive terminal, positive charges accumulate on plate A. The positive charges on plate A repel the additional positive charges that the source tries to deposit on the plate. Thus, the capacitor resists the further build-up of charge on its plates. When the capacitor is fully charged, that is, the plates cannot take any more charges, the capacitor fully resists the current and the current in the circuit falls to 0. The state of a capacitor is known as a steady state. Now let's look at how a capacitor behaves if an AC voltage is applied across it. Consider a capacitor of capacitance C connected to an AC voltage source as shown. the instantaneous AC voltage, V, applied to the capacitor is denoted as V is equal to Vm sin omega t, where Vm is the amplitude of the applied AC voltage. Let this be equation 1. Now assuming the circuit to be purely capacitive, which means it has only a capacitor in the circuit, the instantaneous voltage across the capacitor is equal to the voltage supplied by the AC source. We shall make use of Kirchhoff's loop rule. According to this rule, the sum of potential differences across various components in the circuit is 0. Thus, we have V minus Vm sin omega t is equal to 0, which again leads to equation 1. As instantaneous voltage across the capacitor, V is equal to Q by C, we can write equation 1 as Vm sin omega t is equal to Q by C, or Q is equal to C into Vm sin omega t. Let this be equation 2. We know that current I is the rate of flow of charge in the circuit. That is, I is equal to dq by dt. Let this be equation 3. Substituting equation 2 in equation 3, we get I is equal to d by dt of CVm sin omega t. As C and Vm are constants, and as d by dt of sin omega t is equal to omega cos omega t, we have I is equal to omega Vmc into cos omega t. Let this be equation 4. By trigonometric substitution of cos theta with sin theta plus pi by 2, we get equation 5 as shown. This equation can be represented as I is equal to Im sin of omega t plus pi by 2, where Im is equal to omega Vmc. Let this be equation 6. The amplitude of the current, Im, can also be expressed as amplitude of voltage, Vm, divided by 1 by omega c. Let this be equation 7. Here, 1 by omega c is analogous to resistance and is called capacitive reactance. Capacitive reactance is denoted by Xc. Hence, this term capacitive reactance is denoted by the inverse of the product of angular frequency, omega, and capacitance, C. Let this be equation 8. From equations 7 and 8, we get the amplitude of the current, Im, as the amplitude of the voltage, Vm, divided by the capacitive reactance, Xc. On close inspection of equations 1 and 6, which are derived for the value of current in the circuit, we can see that the current leads voltage in phase by a factor of pi by 2 compared to voltage. The phasor diagrams for analyzing the relationship of lead or lag between current and voltage is as shown. This lead in phase by pi by 2 units is equivalent to a lead in time by 1/4 of time period t. Another thing to note is that the maximum value of the current in the circuit is achieved at exactly 1/4 the time period of every cycle before the maximum value of voltage is achieved. Let us now try to look at power dissipation through the capacitor compared to resistance. The instantaneous power supplied, P, to the capacitor is denoted by the product of voltage with current through any circuit element. Using equations 1 and 4 and the relation Im is equal to omega Vmc, we get P is equal to Vm sin omega t into Im cos omega t. Since sin omega t into cos omega t is equal to 1 by 2 sin 2 omega t, we get P is equal to Vm Im by 2 into sin 2 omega t. Let this be equation 9. This instantaneous power here evaluates as a time-dependent harmonic function. As the average value of sin 2 omega t over one cycle of AC is equal to 0, the average of power P over one complete time period will be 0. Hence, power supplied to a capacitor on average in a circuit is 0. This can be seen as displayed by plotting a graph representing power supplied over time. As shown in the graph, we will study the charging of the capacitor in the 4 time periods marked as 0, 1, 1, 2, 2, 3, and 3, 4 respectively. As in the first time interval, 0 to 1, the value of the current keeps decreasing in the circuit from being maximum at time t is equal to 0 and reaching 0 at 1 at 1/4 of its time period. By the end of this time segment, plate A gets fully charged with positive charges and plate B with negative charges, and they oppose any further current in the circuit. The plates are fully charged at the instance 1. The voltage across the plates is in phase with the charge Q, and peaks at time t is equal to 1. As the current and voltage are both positive, it means that the power is positive. Positive power refers to charging of the capacitor. Hence, power is being absorbed by the capacitor and it gets charged. In the second time interval, 1 to 2, the current changes direction. Thus, the accumulated charges on the plates reduce. The voltage reduces but remains positive. Since the voltage is positive and the current is negative, power is negative. Negative power refers to discharge of the capacitor. Hence, energy previously absorbed by the capacitor is now being returned to the circuit. In short, the capacitor is discharging in this part of the cycle. In the third time interval, 2 to 3, the value of current keeps increasing. Here, as the current now is in the opposite direction compared to the last interval, the charges on the two plates effectively interchange. Plate A is now negatively charged, while plate B holds positive charges. As the current and voltage are both negative, power is positive. Hence, energy is again being absorbed in the capacitor and it gets charged. In the last time interval, 3 to 4, the direction of current again reverses at 3. Thus, the charge begins to deplete from the capacitor plates, thereby reducing the effective voltage across the two plates. The voltage finally becomes 0 at 4. As the voltage is negative, while the current has become positive, it means that the power is negative. Hence, energy is again being released from the capacitor. Thus, finally at the end of the cycle, the capacitor returns to state 0 again. This cyclic discharging and charging of the capacitor, or more precisely, its conducting plates, in reverse polarities keeps taking place as long as AC current is established in the circuit. The instantaneous current and the phase relation between current and voltage of an LCR circuit can be determined using two methods, namely the phasor diagram solution and the analytical solution. In this module, we shall study the phasor diagram solution. Consider a circuit comprising of a resistor of resistance R, a capacitor of capacitance C, and an inductor of inductance L connected in series to an AC source with voltage V equal to Vm sin omega t. Here, Vm is the maximum applied AC voltage and omega is its angular frequency. As per the convention being used, subscript m denotes maximum value or amplitude of the quantity being considered. In the circuit, we see that the applied AC voltage V is the instantaneous voltage across the circuit. At any instant, the charge on the capacitor is Q. The current in the circuit is I, and di by dt represents the rate of change of current in the circuit. Instantaneous voltage across the capacitor is equal to Q by C. The voltage across the resistor is IR, and the induced EMF across the inductor is minus LdI by dt. The negative sign here denotes the direction of the induced current through the conductor according to Lenz's law. Applying Kirchhoff's loop rule to this circuit, we get Q by C plus IR plus LdI by dt minus V equal to 0. Let this be equation 1. Since V is equal to Vm sin omega t, we get Q by C plus IR plus LdI by dt is equal to Vm sin omega t. As we know that the three circuit elements are in series, thus the current I through them is the same. Thus, we have I is equal to Im sin omega t plus phi, where Im is the amplitude of the AC current in the circuit, omega is the angular frequency, and phi is the phase difference. Now we will use the phasor approach to find the expression for the instantaneous current I. Let the instantaneous voltages or potential differences across the three circuit components be VL for the inductor, VR for the resistor, and VC for the capacitor. We know that the voltage in the inductor leads the current in the circuit in phase by pi by 2 in a pure inductive circuit. The phasor diagram for the inductor shows the phase relation between V and I in the inductor. Conversely, the voltage in the capacitor lags the current in the circuit in phase by pi by 2 in a purely capacitive circuit. The phasor diagram for the capacitor shows the phase relation between V and I in the capacitor. The amplitude of the voltage across the resistor is VRM equal to Im into R. The amplitude of the voltage across the inductor is VLM equal to Im into XL, where XL is the inductive reactance of the inductor. We know that XL is equal to omega L. The amplitude of the voltage across the capacitor is VCM equal to Im into XC, where XC is the capacitive reactance of the capacitor. We know that Xc is equal to 1 by omega C. The instantaneous total voltage V in the circuit is equal to the algebraic sum of the instantaneous potential differences across the resistor, capacitor, and inductor, represented as VL, VC, and VR respectively. And this can be vectorially represented as sum of the phasors VL, VC, and VR, which can be calculated as follows. The amplitudes of the potentials across the capacitor and inductor are VC and VLM respectively, and are at a phase difference of pi by 2 from that across the resistor, that is VRM, and they lie on the same line on the phasor diagram. Hence, the phasors VL and VC lie on a line perpendicular to VR, but in directions opposite to each other. Considering the directions of VC and VL on the phasor diagram, we can obtain a single phasor for VC plus VL with the magnitude of VCM minus VLM. Here, we assume that the capacitive reactance Xc is greater than the inductive reactance XL, and hence we have VCM greater than VLM. The phasor with the magnitude VCM minus VLM is at right angles to the phasor with the magnitude VRM. The amplitude of applied AC voltage Vm can be calculated by using Pythagorean theorem on the simplified phasor diagram. Substituting the values, we see that Vm square is equal to Vrm square plus Vcm minus VLM square. Using the values of Vrm, Vcm, and VLM, we get Vm square is equal to Imr square plus Imxc minus Imxl square. Vm square is equal to Im square into R square plus Xc minus XL square. Let this be equation 2. Or we have Vm equal to Im into under root R square plus Xc minus XL square. Now, we have Im equal to Vm by under root R square plus Xc minus XL square, which is equal to Vm by Z. Let this be equation 3. Here, Z is the impedance of the LCR series AC circuit, which is analogous to resistance in a DC circuit, and is equal to under root R square plus Xc minus XL square. Let this be equation 4. The impedance equation can also be written as Z square is equal to R square plus Xc minus XL square. This equation represents a right-angled triangle as per Pythagoras theorem. This triangle is called the impedance diagram. In an LCR series AC circuit, the phase difference phi existing between the voltage and the current can be determined by using the impedance diagram. In the impedance diagram, the hypotenuse gives the impedance Z. Here, we observe that tan phi is equal to Xc minus XL by R. Let this be equation 5. Phase difference phi is equal to tan inverse of Xc minus XL by R. Thus, the current flowing through the LCR series AC circuit can be given as I equal to Im sin omega t plus phi where Im is given by equation 3 and the phase difference phi can be calculated from the equation 5. Hence, we have obtained information of all the entities we desired using the phasor approach to the LCR circuit. Consider a circuit comprising of a resistor of resistance R, a capacitor of capacitance C, and an inductor of inductance L connected in series to an AC source, which applies a voltage V equal to Vm sin omega t at any instant of time t. Here, AC voltage V is the instantaneous voltage existing in the circuit. At any instant of time, the charge on the capacitor is Q. The current in the circuit is I, and di by dt represents the rate of change of current in the circuit. Instantaneous voltage across the capacitor is equal to Q by C. The voltage across the resistor is IR, and the induced EMF across the inductor is minus LdI by dt. The negative sign here signifies the direction of the induced current according to Lenz's law. Applying Kirchhoff's loop rule to this circuit, we get Q by C plus IR plus LdI by dt minus V equal to 0. Let this be equation 1. Since V is equal to Vm sin omega t, we get Q by C plus IR plus LdI by dt is equal to Vm sin omega t. We know that the instantaneous current I is equal to dq by dt. Hence, we get Q by C plus R dq by dt plus LD square Q by dt square is equal to Vm sin omega t. Let this be equation 2. As the three circuit elements, the resistor, the capacitor, and the inductor are in series, the current through them is same in amplitude as well as in phase. Let us now assume a solution for the equation 2 as Q is equal to Qm sin omega t plus theta, where Qm and theta are constants. Qm is the maximum charge on the capacitor. Then, we have I equal to dq by dt is equal to Qm omega cos omega t plus theta. Let this be equation 3. Similarly, we have d square q by dt square equal to minus Qm omega square sin omega t plus theta. Substituting these values in equation 2, we get Qm sin omega t plus theta by C plus R Qm omega cos omega t plus theta minus L Qm omega square sin omega t plus theta equal to Vm sin omega t. Taking omega Qm common in the left-hand side of the equation and rewriting the expression, we get omega Qm into sin omega t plus theta by omega c plus R cos omega t plus theta minus omega L sin omega t plus theta is equal to Vm sin omega t. Since capacitive reactance Xc is 1 by omega c and inductive reactance XL is equal to omega L, we can write the above relation as omega Qm into Xc sin omega t plus theta plus R cos omega t plus theta minus XL sin omega t plus theta equal to Vm sin omega t. Or omega Qm into R cos omega t plus theta plus xc minus xl into sin omega t plus theta equal to Vm sin omega t. Let this be equation 4. Similar to resistance in a DC circuit, we introduce a quantity impedance in AC circuits, denoted by Z. Here, Z is the impedance of the LCR series AC circuit and is expressed as Z is equal to under root R square plus XC minus XL square. In equation 4, multiplying and dividing the left-hand side by the impedance of the circuit Z, we get the equation 5. If sin phi is the difference of capacitive and inductive reactance divided by the circuit impedance, that is, sin phi is equal to XC minus XL by Z, where phi is the phase difference between the instantaneous current and the voltage. Then, cos phi gives the relation between the resistance with the circuit impedance, that is, cos phi is equal to R by Z. Now, sin phi by cos phi will be equal to tan phi, which will be equal to XC minus XL by R. If the relations between Z, R, and XC minus XL are represented through a diagram, they form a right-angled triangle as shown. This is called the impedance diagram. From the impedance diagram also, we observe that tan phi is equal to XC minus XL by R. Hence, we get the same relation for phi as was obtained through the phasor approach that we learned earlier. Substituting the values of cos phi and sin phi in equation 5, we get Qm omega z cos phi cos omega t plus theta plus sin phi sin omega t plus theta is equal to Vm sin omega t. This can now be written as Qm omega z cos omega t plus theta minus phi equal to Vm sin omega t. Let this be equation 6. Here, we have used the trigonometric transformations identity cos A cos B plus sin A sin B is equal to cos of A minus B. Comparing the values on both the sides of equation 6, we get Vm equal to Qm omega z, which is equal to Imz. Therefore, maximum voltage in the LCR circuit, Vm, is equal to maximum current in the circuit, Im, into impedance of the circuit Z. Also, as cos omega t minus pi by 2 is equal to sin omega t, we have theta minus phi is equal to minus pi by 2. From equation 3, for the instantaneous current I is equal to Qm omega cos omega t plus theta. Since Im is equal to Qm omega, we get I equal to Im cos omega t plus theta. Since theta minus phi equal to minus pi by 2, we have theta is equal to phi minus pi by 2. We can simplify the above equation as I equal to Im cos omega t plus phi minus pi by 2. Thus, we have the instantaneous current in an LCR circuit. I is equal to maximum current in the circuit, Im into sin omega t plus phi. To know the maximum value of the current in LCR circuit, we use the equation for maximum current Vm is equal to IMZ. Substituting the value of the impedance Z, we get Im equal to Vm by under root of R square plus Xc minus XL square. Thus, the relations finally obtained from the analytical approach towards computing the unknowns in the LCR circuit are the same as computed through the phasor approach. This analytical approach can be regarded as a pure algebraic approach, whereas phasor approach is more of a geometrical one. Resonance is a phenomenon observed in systems that tend to oscillate at some fixed frequency. This frequency is called the natural frequency of the system. If the system oscillates at its natural frequency under the influence of an external periodic force, then the amplitude of the oscillations is noticeably larger than those at other frequencies. Consider 4 pendulums P, Q, R, and S suspended from a rigid support as shown. The lengths of the pendulums P and Q are equal. The lengths of the other 2 pendulums R and S are different from that of P and Q. Initially, all the pendulums are at rest and hence do not oscillate. When the pendulum P is made to oscillate, after a certain period of time, all the other 3 pendulums oscillate as well. Here, the oscillation is due to an external force, which is from the pendulum P. Out of the 3 pendulums Q, R and S, the length of pendulum Q is equal to that of pendulum P. Hence, the natural frequencies of these 2 pendulums are equal, and this gives rise to the situation where the pendulum Q oscillates with increasing amplitude due to resonance. This is an example of resonance in mechanical systems. Similarly, the phenomenon of resonance can also be observed in electrical systems. Let us now study about the phenomenon of resonance in an LCR series circuit. We have seen that at any instant t, the applied AC voltage is represented as V equal to Vm sin omega t, where Vm is the amplitude of the AC voltage and omega is its angular frequency. At the same instant, the current in the circuit is given as I equal to Im sin omega t plus phi, where phi is the phase difference between the AC voltage and the current. The phase difference, phi, can be calculated by the expression tan phi equal to Xc minus XL by R, where Xc is the capacitive reactance, XL is the inductive reactance, and R is the resistance. We know that the amplitude of current Im in an LCR circuit is given by Vm by Z, where Z is the impedance of the circuit. In terms of capacitive reactance Xc and inductive reactance XL, we have Z is equal to square root of R square plus Xc minus XL square. Substituting the value of Z, we get Im as Vm by square root of R square plus Xc minus XL square. Let this be equation 1. We also know that Xc is equal to 1 by omega c and XL is equal to omega L. For resonance in an LCR series circuit, the amplitude of the current in the circuit should be the maximum. For this, the necessary condition is Xc should be equal to XL. Substituting the values of Xc and XL in the expression, which is the condition for resonance, we get 1 by omega c equal to omega L, or omega square equal to 1 by LC. On further simplification, we get omega is equal to 1 by square root LC. Let this be equation 2. Let us now call this angular frequency as omega naught. This frequency is also referred to as the resonant frequency of the circuit. We observe that as omega is varied, the value of current changes and is maximum when the value of omega is equal to omega naught, such that XC is equal to XL. As the impedance Z of the circuit minimizes and becomes equal to R. This is the condition for resonance. Now, equation 1 can be written as Im is equal to Vm by R. Thus, we observe that when the angular frequency omega of applied AC voltage becomes equal to the resonant frequency omega naught, the amplitude of current Im reaches its maximum. Resonance is possible only in a circuit which has both capacitive and inductive components, as the condition Xc is equal to XL needs to be satisfied. Thus, resonance can be observed in a series LCR circuit or in a series LC circuit, and cannot be observed in RC or RL circuits. This can also be observed from the graph of Im plotted against omega, with Im on the y-axis and omega on the x-axis. Here is a sample graph for the amplitude of current Im versus angular frequency omega, plotted for the values L is equal to 1 millihenry, C is equal to 1 nanofarad of an LCR circuit with two different values of resistance R. The first plot is for the value R equal to 100 ohm, and the second one for R equal to 200 ohm. The amplitude of the source voltage Vm is taken equal to 100 volt. For the given set of values of L and C, we find that the value of omega naught is equal to 10 power 6 radian per second, which is equal to 1 mega radian per second. From the graph, we see that the amplitude of the current in an LCR circuit is the maximum when the angular frequency omega naught is equal to 1 by root LC for either of the resistance values. For other values of the frequency, the amplitude of the current is less than that at the resonant frequency. We also observe that except for the case of resonance, for every single value of Im, there are two values of angular frequency omega 1 and omega 2 respectively, one lesser and one greater than omega naught, which lies symmetrically on either side of omega naught. Let us consider the specific case of the frequency at which the amplitude of the current is 1 by root 2 times the maximum value of the amplitude of current, I max, at natural frequency. Let the corresponding angular frequencies be omega 1 and omega 2. From the graph, we have omega 1 is equal to omega naught minus delta omega, and omega 2 is equal to omega naught plus delta omega, where delta omega is the difference between omega naught and omega 1 or omega 2. Hence, the difference between omega 2 and omega 1 is equal to 2 delta omega. This is known as the bandwidth of the circuit. The ratio of omega naught to 2 delta omega is a measure of the sharpness of the resonance. A larger ratio indicates a sharper resonance. Let us now calculate the value of delta omega using equation 1 for the angular frequency omega 2. Since amplitude of current is 1 by root 2 times the maximum current at resonance, we get I max by root 2 is equal to Vm by R into root 2. On simplifying, we get omega 2L minus 1 by omega 2C is equal to R. Substituting the value of omega 2 is equal to omega naught plus delta omega in this equation, and simplifying, we get equation 3 as shown. Using binomial approximation on the expression 1 by 1 plus delta omega by omega naught in equation 3, we get equation 4 as shown. On simplifying this equation, we get delta omega is equal to R by 2L. Using the value of delta omega obtained, the sharpness of the resonance, omega naught by 2 delta omega, can now be written as equal to omega naught L by R. This is also referred to as the quality factor Q of the circuit. Since omega naught L is equal to 1 by omega naught C for resonance, we can also write equation 4 as Q is equal to 1 by omega naught CR. Let this be equation 5. From the expression omega naught by 2 delta omega is equal to omega naught L by R, and the expression Q is equal to omega naught L by R, we get the bandwidth of the circuit as 2 delta omega is equal to omega naught by Q as shown. This indicates that a higher value of the quality factor leads to a sharper resonance as the bandwidth decreases. One of the important applications of LCR series resonance is in the tuning of radio and TV receivers. The circuit diagram shows a typical arrangement consisting of an LCR series circuit used for receiving signals. In this arrangement, the antenna receives various signals and feeds it to the input. This induces a signal at the coil of inductance L in the LCR series circuit. While tuning, the capacitance in the circuit is varied, such that the resonant frequency of the circuit becomes nearly equal to that of frequency of the radio signal being fed at the input for a particular value of the capacitance. Now, the amplitude of current in the circuit becomes the maximum, and we get a high quality factor as delta omega is the minimum at resonance. In this manner, the LCR series circuit can be used to tune into a large number of frequencies of signals in radios and televisions. We observe that when the resonance is less sharp, the selectivity of the circuit will be lesser, as there will be a large range of delta omega frequencies for which the LCR series circuit will be close to resonance. We also observe that for a large quality factor, we should have large value of L or a low value of R for the expression Q is equal to omega naught L by R. Let us consider an LCR circuit for calculating the power dissipation in the circuit. If the voltage applied across the circuit V is equal to Vm sin omega t, where Vm is the amplitude of the applied AC voltage, omega is the angular frequency of the applied AC at time t, then the current I is equal to Im sin omega t plus phi, where Im is the amplitude of the AC current passing through the circuit and phi is the phase difference between the applied AC voltage and the AC current. We know that in an LCR AC circuit, impedance Z is equal to square root of R square plus XC minus XL square and Im is equal to Vm by Z. Here, XC is the capacitive reactance and XL is the inductive reactance of the circuit. Substituting the value of Z, we get Im as in equation 1. From the impedance diagram of an LCR circuit, tan phi is equal to XC minus XL by R. Let this be equation 2. And cos phi is equal to R by Z. Let this be equation 3. We know that the power dissipated in a circuit is the product of the voltage and current in the circuit. Substituting the values of the instantaneous AC voltage V and AC current I, we get the instantaneous power P is equal to V into I, or P is equal to Vm sin omega t into Im sin omega t plus phi. Using the trigonometric identity, 2 sin A sin B is equal to cos A minus B minus cos A plus B, or sin A sin B is equal to half cos A minus B minus cos A plus B. We get sin omega t into sin omega t plus phi is equal to half into cos omega t minus omega t plus phi minus cos omega t plus phi. On further simplification, we get sin omega t into sin omega t plus phi is equal to half into cos phi minus cos 2 omega t plus phi. Thus, the instantaneous power P can be written as Vm by 2 into cos phi minus cos 2 omega t plus phi. Let this be equation 4. The average power dissipated over a cycle is given by the average of the right-hand side of the equation 4. Here, only cos 2 omega t plus phi is time dependent. However, its average over an entire cycle is 0, as the average value of a cosine function over a complete cycle is 0. Hence, the average power PAV is equal to Vm by 2 into cos phi. Let this be equation 5. The same expression can be written as Vm by root 2 into Im by root 2 into cos phi. We know that RMS values of the AC voltage and the current are given as Vrms is equal to Vm by root 2 and IRMS is equal to Im by root 2. Thus, average power dissipated PAV is equal to Vrms IRMS cos phi. Let this be equation 6. Since Vrms is equal to Irms into Z, we can write average power PAV is equal to Irms square into Z cos phi. This shows that the power dissipation is dependent not only on the voltage and current in the circuit, but also on the cos of the phase angle phi between them. The term cos phi is called the power factor for the system. Let us observe the variation in the power dissipation across various AC circuits based on variation in the power factor. If a circuit has only a resistor, it is called a purely resistive circuit. In this case, since the phase difference between the AC voltage across the resistor VR and the current I is 0, that is, the value of cos phi is 1, it implies that the power factor is maximum or unity. Hence, power dissipation is the highest in a purely resistive circuit. If a circuit is purely inductive, then the value of phi is plus pi by 2. That is, the voltage across the inductor VL leads the current I by pi by 2. Since cos pi by 2 is 0, we can say that the power factor of a purely inductive circuit is 0. In other words, there is no power dissipation in a purely inductive circuit. If a circuit is purely capacitive, then the value of phi is minus pi by 2. That is, the voltage across the capacitor VC lags the current I by pi by 2. The value of cos minus pi by 2 is equal to cos pi by 2, which is equal to 0. Hence, the power factor of a purely capacitive circuit is 0. In other words, there is no power dissipation in a purely capacitive circuit. The current in a purely inductive or purely capacitive circuit, where the power dissipation is 0, is known as wattless current. In the case of CR, LC, LCR series AC circuits, there exists a phase difference between the AC voltage V and current I in the range of 0 to pi by 2. Hence, the value of the power factor will be non-zero but less than 1. Hence, the power dissipation in these types of circuits is non-zero. The average power dissipated in an LCR series AC circuit is expressed by equation 6, where the power factor cos phi is equal to R by Z as in equation 3. In this case, the power dissipation is only through the resistor. If the LCR series AC circuit is in resonance, that is, the capacitive reactance XC is equal to the inductive reactance XL, and then we know that the value of tan phi reduces to 0. This implies that the value of phi is 0 and hence the power factor cos phi is equal to 1. Hence, the power dissipation in an LCR circuit is the maximum as the power factor becomes unity. The average power, in this case, is equal to the product of Vrms and Irms. To improve the power factor of a circuit, we often introduce an appropriate capacitor or inductor to cancel the predominance of the other in the circuit, thereby letting the impedance Z of the circuit get closer to the resistance of the circuit. Thereby, we can have Z equal to R, which implies that cos phi is equal to R by Z, equal to 1, which is the power factor at resonance. This is beneficial in many industrial applications. For example, when the distance is large, power is transmitted at very high voltages in order to minimize dissipation. This is so because a higher voltage implies lower current and subsequently lower power loss. The phenomenon of LC oscillations can be observed when a charged capacitor is placed in series with an inductor in a circuit. Consider a fully charged capacitor with plate A charged positively and plate B charged negatively, connected to an ideal inductor of inductance L. When the circuit is closed, the capacitor starts discharging through the inductor and discharges as long as a potential difference exists between the two capacitor plates. The current in the circuit is from A to B through the inductor. The potential difference across the capacitor is equal to that across the inductor. Gradually, the capacitor discharges and the potential difference between the plates as well as that across the inductor becomes zero. During the time interval, when the potential difference reduces from maximum to minimum, there is an induced EMF, which opposes the passing current in the inductor. Now, the magnetic field around the inductor starts decreasing, and this induces a current from B to A in the circuit according to Lenz's law. This induced current in the circuit, which is from plate B to plate A, charges the capacitor in the opposite sense, with plate B now positive and plate A negative. This induced current exists as long as the magnetic field exists around the inductor. By the time the magnetic field reduces to zero, the capacitor becomes fully charged. The capacitor again starts discharging, but now the current in the circuit is from plate B to plate A. This builds up the magnetic field in the inductor, but this time the polarity is reversed. Gradually, the capacitor discharges fully, and the magnetic field around the conductor grows to its strongest. Again, the magnetic field around the inductor starts decreasing, this time inducing a current in the opposite direction. This occurs until the magnetic field exists around the inductor. By this time, however, the capacitor returns to its original, fully charged state, with plate A positively charged and plate B negatively charged. Thus, we observe that the capacitor's charging and discharging is oscillatory in nature. Now, let us obtain an expression for the natural frequency of these oscillations in the LC circuit. Let Qm denote the maximum charge on the capacitor at time t equal to 0. At this instance, the current in the circuit and the induced EMF across the inductor are equal to 0. If Q is the charge on the capacitor and I is the current in the circuit at a time t, then the potential difference across the capacitor is the ratio of Q to C, where C is its capacitance. the induced EMF across the inductor is L di by dt. By applying Kirchhoff's law for the circuit, we get Q by C minus L di by dt is equal to 0. Let this be equation 1. As the charge Q on the capacitor decreases, the current in the circuit dQ by dt becomes negative. Equation 1 now becomes Q by C minus LD by dt of minus dQ by dt is equal to 0. This can be written as d square Q by dt square plus Q by LC is equal to 0. Let this be equation 2. We learnt earlier that the equation of motion for a particle of mass m in simple harmonic motion along the x-axis with a natural angular frequency omega naught is d square x by dt square plus omega naught square x is equal to 0. Let this be equation 3. Here, the natural angular frequency omega naught is equal to the square root of k by m, where k is the force constant for simple harmonic motion. Equation 2 is observed to be similar to equation 3. Comparing equations 2 and 3, we have the natural frequency omega naught of LC oscillations in the circuit equal to 1 by square root of LC. We know that in equation 3, the displacement x is expressed as a cos omega naught t plus phi, where phi is the phase difference and a is the amplitude of oscillations. Similarly, for equation 2, the charge q can be expressed as q is equal to qm cos omega naught t plus phi, where qm is the maximum charge on the capacitor. Let this be equation 4. At time t equal to 0, the charge q on the capacitor has the maximum value qm, which means that the value of the cos phi has to be 1, and hence phi has to be 0. Hence, equation 4 now becomes q is equal to qm cos omega naught t. Let this be equation 5. As the capacitor gets discharged with time, we get current I is equal to minus dq by dt. Substituting the expression for charge from equation 5 and simplifying, we get I is equal to Im sin omega naught t, where Im is equal to omega naught into qm. Let this be equation 6. Now let us analyze the LC oscillations from an energy point of view. At any instance, the energy stored in the capacitor U is equal to Q square by 2C. And the energy stored in the inductor U dash is equal to half Li square. From our previous analysis, we know that at any given time t, the charge Q is equal to Qm cos omega naught t. The current I is equal to Im sin omega naught t, where Im is equal to omega naught qm, and omega naught is equal to the square root of 1 by LC. Rearranging omega naught in the expression, we get L is equal to 1 by omega naught square C. The total energy, U total of the circuit, is the sum of the energy stored in the capacitor and the energy stored in the inductor. Thus, U total is equal to Q square by 2C plus half Li square. Substituting the values of I and Q in this expression and simplifying. We get U total is equal to Qm square by 2C. This expression of total energy is equal to the energy stored in the capacitor when it is fully charged, which was the initial stage. Thus, the total energy in an LC circuit is always a constant. This also holds good as no external force acts on the system. Hence, this oscillation is self-sustained. We also observe that LC oscillations are very similar to the mechanical oscillations of a body in simple harmonic motion. In the case of a spring, when the spring is initially in an elongated position, all the energy of the system is in the form of potential energy. When the spring is released and it reaches the mean position, this potential energy in the system is converted completely into kinetic energy. When the spring goes to the other extreme, the kinetic energy in the system is again converted back into potential energy for the spring. In a similar manner, in LC oscillations, the energy oscillates between the electric field due to the capacitor and magnetic field due to the inductor. These LC oscillations sustain infinitely if all the elements in the circuit are ideal in nature. That is, the inductor has zero resistance and the capacitor is characterized by a single constant value called capacitance. However, in a practical situation, this is not true. Actually, the inductor also has some resistance, which leads to the damping of these oscillations. Similarly, neglecting the radiations emitted by the system also renders this analysis quite unrealistic. From our discussion of LC oscillations, we can draw the following analogies between a mechanical and an electrical system. We see that the inductance L is similar to mass. The value of 1 by C is similar to force constant K. Force constant K is the restoring force per unit displacement, whereas 1 by C is the value of the potential difference required to store unit charge. Charge Q is analogous to displacement x, which implies current I is analogous to velocity v. The total energy in both systems remains constant or is conserved. The effect of damping on the LC oscillations can be compared to that of a simple harmonic oscillator. A transformer is a device used to increase or decrease the voltage of an alternating current. It is used in power transmission to reduce the power losses and to increase the efficiency of power supply. Transformers work on the principle of mutual induction. According to the principle of mutual induction, when two coils are placed close to each other and if one of the coil carries a time-varying current, a current is induced in the other coil. A transformer comprises of two coils, C1 and C2, insulated from each other. These coils are wound over a soft iron core. The soft iron core is provided to increase the magnetic flux through the coils and to provide a medium through which all the magnetic flux through the primary coil also passes through the secondary coil. This increases the mutual inductance of the two coils as more flux from the first coil now passes through the second coil. If the time-varying magnetic flux produced by coil C1 passes through the other coil C2, an EMF E is induced in coil C2. The EMF induced in the coil C2 is equal to minus M di by dt, where di by dt is the rate of change of current in the coil C1 and M is the mutual inductance of the coils. The negative sign here indicates the direction in accordance with Lenz's law. The coil C1, at which input voltage is applied, is called the primary coil, and the coil C2, at which output voltage is obtained, is called the secondary coil. Let the number of turns in these coils be NP and NS respectively. Let us consider the case of an ideal transformer where the primary coil has negligible resistance and all the magnetic flux in the core links both the primary and the secondary windings. In such a case, the energy in the transformer and the core are zero. Then, due to mutual induction, the induced EMF or voltage in the secondary coil ES is directly proportional to the number of turns NS in it. Then, according to the principle of mutual induction, the EMF ES is equal to minus NS into d phi by dt, where d phi by dt is the rate of change of the magnetic flux linked with the secondary coil. The minus sign is in accordance with Lenz's law. The alternating flux phi also induces an EMF referred to as the back EMF in the primary coil due to self-induction. This EMF EP is proportional to the number of the turns NP in the primary coil. This back EMF EP is equal to minus NP into d phi by dt, where d phi by dt is the rate of change of the magnetic flux linked with the primary coil. The minus sign is in accordance with Lenz's law. For an ideal transformer, the primary coil has zero or negligible resistance. Therefore, the induced EMF EP is equal to the voltage across the primary VP. Hence, we get VP is equal to minus NP into d phi by dt. Let this be equation 1. If the current taken from the secondary coil is small, as it is an open circuit, then, to a good approximation, we get induced EMF ES equal to voltage across the secondary coil Vs. Hence, we have Vs is equal to minus Ns into d phi by dt. Let this be equation 2. Dividing equation 2 by 1 and simplifying, we get Vs by Vp equal to Ns by Np. Let this be equation 3. Thus, we observe that the ratio of the voltage across the secondary coil to that across the primary coil of a transformer is the same as the ratio of the number of turns in the secondary coil to that in the primary coil, respectively. Assuming the transformer to be 100% efficient, that is, there are no energy losses, then the input power is equal to the output power. This is a good approximation, since a well-designed transformer may have an efficiency of more than 95%. 100% efficiency is not practically possible because of various losses. We know that power P is the product of the current I and the voltage V. Hence, we get P is equal to IV. Now, for an ideal transformer, we have power in the primary coil, PP, is equal to power in the secondary coil, PS. Let this be equation 4. This can be written as IP into VP is equal to IS into VS. Or VS by VP is equal to IP by IS. Let this be equation 5. From equations 3 and 5, we get Vs by Vp is equal to Ip by Is is equal to Ns by Np. Let this be equation 6. This shows that the current in the coils is inversely proportional to the number of turns in the coil. Since I and V both oscillate with the same frequency as the AC source, equation 6 also gives the ratio of the amplitudes or RMS values of the corresponding quantities. Now, we can write the voltage and current in the secondary coil in terms of the voltage and current in the primary coil as shown. Let these be equations 7 and 8 respectively. If the secondary coil has a greater number of turns than the primary, the voltage is stepped up. That is, output voltage is higher than the input voltage. This type of transformer is called a step-up transformer. In this type of a transformer, there is less current in the secondary coil than in the primary coil. For example, if the primary coil of a transformer has 100 turns and the secondary has 200 turns, Ns by Np is equal to 2 and Np by Ns is equal to half. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 440 volt. In other words, it is stepped up to 440 volt output at a current Is equal to 5 ampere. Conversely, if the secondary coil has lesser turns than the primary coil, the transformer is called a step-down transformer. Output voltage is lesser than the input voltage. That is, the voltage is stepped down or reduced and the current is increased. For example, if the primary coil of a transformer has 200 turns and the secondary has 100 turns, Ns by Np is equal to half and Np by Ns is equal to 2. Thus, a 220 volt input voltage Vp at input current Ip of 10 ampere gives an output voltage Vs of 110 volt. That is, a step down to 110 volt output at a current Is equal to 20 ampere. These equations apply only to ideal transformers as we assumed. However, in practical situations, all transformers incur small energy losses due to various factors such as flux leakage, resistance of winding wires, eddy currents, and hysteresis. Flux leakage can never be completely eliminated. as not all the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. To minimize the flux leakage, the primary and the secondary coils are wound one over the other. As the wires used for the windings have some internal resistance, some energy is lost due to heat produced in the wire whenever a current passes through them. In high current, low voltage windings, this loss can be minimized by using thick wires. Due to changing magnetic flux in conductors, induced currents known as eddy currents are produced in them. The alternating magnetic flux induces eddy currents in the iron core. The eddy current in these closed loops results in generation of heat and loss of energy. This effect can be reduced by having a laminated core. The alternating magnetic field repeatedly results in the reversal of the magnetization of the core, which consumes some energy due to heating of the core. This is called hysteresis loss. This loss can be minimized by using a magnetic material which has a low hysteresis loss. For transmitting electricity over long distances, we use transformers. First, we use a step-up transformer to increase the voltage and consequently decrease the current in the transmission lines. This reduces the loss of energy as heat. Voltages are then stepped down at various substations and utility poles before it reaches our homes in the range of 220 to 240 volt. There is a practical upper limit to the voltages we can use for transmitting the electrical energy through the transmission lines. Excessive voltages can ionize the air around the transmission lines. This in turn can create a conducting path to the ground or other objects near it, and also can possibly cause damage to life and property in its vicinity. Hence, long strings of insulators are used to keep the transmission lines away from the towers supporting them, and insulators are also used to maintain separation between the wires.